Welcome to Grandpa's Late Nights. It's good to have you here again. Come on in, settle down, get yourself comfortable. Pull the blanket up over your shoulders if the night's got a chill to it, and let that pillow take the whole weight of your head. There's nowhere you need to be right now. Nothing you have to fix, nothing you have to remember in the morning. Just the sound of an old man's voice and a long, slow story to drift off inside of. And before we go any further, I've got a small thing to ask, the same small thing I always ask. If you like these late-night wanderings of mine, if this quiet little channel has become a part of how you get to sleep, a gentle tap on that like button and a quiet subscribe really does help an old timer keep the porch light on. And to those of you who've already done it, thank you, truly, you keep this place warm. So tell me, before your eyes get too heavy, where in the world are you listening from tonight? What time is it in your corner of things? A little apartment in a big loud city, a farmhouse where the only sound is the wind, a bunk on a train somewhere between two towns you'll never see in daylight. I like to picture you all out there, scattered across the dark side of the world, all of us awake together for a little while. Now here's my promise to you, and I mean it every time. We are going to go slow tonight. Slower than slow. I am not going to rush you anywhere. If you drift off before I'm halfway through, and I hope you do, that's exactly as it should be. The story will still be here. The universe isn't going anywhere. You won't miss a single thing that matters, because none of it is a test. And there's nothing to grasp, nothing to hold on to with white knuckles. Let the ideas float past you like leaves on slow water. Some you'll catch, most you'll let go by. That's the whole point. And I'll be honest with you, the way I always am. Tonight's story is a wonder. It's the kind of thing that, if I let myself, could keep me up half the night, just turning it over. So I'll try my best not to make it so interesting it keeps you awake. But if it does, well, at least you'll have learned how human beings figured out the size of the whole universe. That's a fair trade, I think. A fair trade for a night's sleep. So here's where we're headed, gently, one small step at a time. Tonight I want to tell you how we, little soft creatures on a small wet rock, worked out the distances to things we can never touch, never reach, never fly to in 10,000 lifetimes. The distance to the sun, the distance to the stars, the distance to other galaxies, so far away that the light leaving them started its journey before there were people to look up. We're going to climb a kind of ladder together, a ladder made of clever tricks, one rung at a time, from the ground right up into the deep dark. And I'm going to tell you a secret about that ladder as we go, a secret that most folks never mention, and it's the most beautiful and the most frightening part of the whole thing. But we'll get there. No rush. We've got all night. Let me start with the thing that keeps me up, if anything does. Here it is, everything, and I mean everything, that we think we know about the size of the universe is borrowed. It's all leaning on one single measurement, and that measurement is smaller than you'd ever guess. It's the width of the Earth's path around the sun, the size of our own little orbit. That's the foundation. That's the stone the whole cathedral sits on. Every distance to every star, every galaxy, every exploding sun a billion years away, all of it is built up, step by step, from that one baseline. And how big is that baseline, really, in a way you can feel? Well, light, the fastest thing there is, quick enough to go around the whole Earth 7 times in a single second. Light takes about 8 minutes to cross the gap from the sun to us. 8 minutes. That's the whole footing. The entire universe, measured out from a distance, a beam of light strolls across before your tea's finished steeping. Doesn't that just make you want to hold your breath a little? The biggest thing there is, measured from one of the smallest steps we could find. But I'm getting ahead of myself. Let me slow down. Let me take you all the way back to the very bottom of the ladder, to the ground itself, and we'll climb up from there together, gentle as anything. Now, before you can measure the distance to a star, you have to be able to measure the distance to your own front yard. You have to start with things you can walk to, or nearly. And the oldest of these clever tricks, older than you'd believe, goes back to a man named Eratosthenes more than 2,000 years ago. Around the year 240 before the Common Era, think of that, 22 centuries back. This fellow was living in Egypt, and he did something so simple it almost sounds like a child could have thought of it, except nobody had. He'd heard that in one city, at noon on a certain day of the year, the sun shone straight down a deep well and lit up the water at the very bottom. Straight down, no shadow at all. But in another city, far to the north, at that very same moment, a tall stick standing straight up did cast a shadow. A little one, but a real one. Now sit with that for a second, the way he must have. If the earth were flat as a table, the sun's light would hit both places at the same angle, and either both would have shadows or neither would. But one had a shadow, and one didn't. And the only thing that explains that is that the ground itself is curved between the two cities. The earth is round. And here's the loveliest part. From the size of that one little shadow, and knowing how far apart the two cities were, Eratosthenes figured out how big the whole earth is. The size of the entire planet worked out from the length of a shadow and a walk between two towns. He got remarkably close to the real number, 2. That's the first rung, really. The very bottom of the ladder is the size of the earth itself, measured with sunlight and a stick. And there's a mathematician in our own time, a fellow named Terence Tao, sharp as they come, who gave a famous talk about this whole climb we're taking tonight. He called it the cosmic distance ladder, and he traced it right back to Eratosthenes and his shadows. I've always liked that. The ladder into the stars starts with a man measuring a shadow on the ground. And he wasn't alone in that ancient cleverness. Around the same stretch of history, a little earlier even, there was Aristarchus of Samos, about 270 years before the Common Era. This one looked up at the moon and asked a question most people never bother to ask. When the moon is exactly half lit, you've seen it, that clean straight line down the middle, half bright, half dark. Well, Aristarchus realized that at that exact moment, the sun, the moon, and the earth must be sitting at a particular angle to one another, a right angle, out at the moon. And from the shape of that triangle, he reasoned that the sun had to be much, much farther away than the moon, and much, much bigger. Now his numbers were off, he didn't have the tools to measure the angle precisely, and a tiny error in the angle throws the answer way off. But listen, the method was right. The thinking was right. He was doing geometry with the sky, drawing triangles between worlds, and that same kind of triangle is still, to this very day, how we do it. He just didn't have the sharp enough eyes. The idea was already there, 2,000 years early. And then there was Hipparchus, around 150 years before the Common Era, and this one I've got a real fondness for. Hipparchus wanted to know how far away the moon was, and he used an eclipse to do it. When the earth passes between the sun and the moon, it throws its shadow across the moon's face. And by watching how the curve of that shadow fell, how big the Earth's shadow was compared to the moon, and knowing how the geometry had to work, he came up with a number. He reckoned the moon sat about 60 Earth radii away, 60 times the distance from the center of the Earth out to its surface. And here's the thing that gives me a little shiver every time. The real answer, the one we know today with all our lasers and satellites, is about 60 1/3 Earth radii. He was almost dead on. 2,000 years before anyone could fly, a man worked out the distance to the moon by watching a shadow fall across it during an eclipse, and he got it right to within a whisker. That's not luck. That's the human mind doing what it does best, noticing and reasoning and refusing to just shrug and say we'll never know. So that's the deep foundation, the old triangulators, the people who first understood that you don't have to travel somewhere to measure how far away it is, you just have to be clever about angles and shadows. But for all their brilliance, there was one number that stayed slippery for a very, very long time. And it's the most important number of the whole climb. It's the distance from the Earth to the Sun. We even gave it a special name because so much depends on it. We call it the Astronomical Unit, the AU. It's the mean distance between the Earth and the Sun, and everything above it on the ladder is measured in multiples of it, or worked out through it. It is the ruler. It is the yardstick that all the other yardsticks are cut from. And for most of human history, we did not know how long that ruler actually was. Let me tell you how hard people worked to get it, because it's a wonderful, slightly mad chapter. For a long stretch, the best way anyone had to pin down that sun distance was to watch the planet Venus cross in front of the sun. Once in a great while, and I mean rare, painfully rare, Venus passes directly between us and the sun, and you can see it as a tiny black dot creeping slowly across that huge bright face. A transit, they call it. And if you time that crossing very carefully, and you do it from two far-apart places on the Earth at once, the little differences in what you see can be turned, through geometry, into the distance to the sun. It's the triangle trick again, just aimed at a passing planet. But here's the catch, and it's a heartbreaker. These transits of Venus don't come around often. They come in pairs, 8 years apart, and then you wait more than a century for the next pair. So in the 1700s and 1800s, whenever one was due, whole nations packed up expeditions and sent astronomers sailing to the far corners of the Earth just to catch it. There were transits in 1761 and again in 1769. Then a long, long wait, and another pair in 1874 and 1882. Think of those men, hauling brass telescopes across oceans, camping on remote islands, all to watch a black dot crawl across the sun for a few hours, because those few hours were the only chance in their lifetime to measure the size of the ruler that measures everything. Some of them sailed for months and then got clouded out. Rain on the one day. A whole voyage undone by weather. It's enough to break your heart, and it happened more than once. And even with all that effort, all those expeditions, the answers still didn't quite agree. They'd come back with numbers that differed by a fraction of a percent, and in this business, a fraction of a percent is a great deal. Later on, folks tried another approach, using a little asteroid called Eros that swings fairly close to the Earth. They measured its shifting position against the stars around the turn of the century in 1900 and 1901, and again in the early 1930s. That tightened things up. But still, the foundation stone of the whole ladder wobbled just a little. We were building a staircase to the edge of the universe on a bottom step we couldn't quite measure clean. And then, in 1961, something changed everything. And it's my favorite kind of change, because it's so beautifully direct. No more triangles, no more sailing to islands, no more waiting 100 years for a planet to line up. In 1961, several teams, some at a place called the MIT Lincoln Laboratory, some at the Jet Propulsion Laboratory, and teams over in the Soviet Union too, all working on this. They did something wonderfully simple in idea, though fiendishly hard in practice. They took a radar beam, radio waves, the same family of thing that carries a voice to your telephone, and they aimed it straight at the planet Venus. And they sent it out into the dark, and they waited. Because here's the thing you can build a whole universe on. We know exactly how fast that beam travels. The speed of light, and radio waves are light, just a color your eyes can't see, is a fixed known number. It's 299,792,458 meters every second. Exactly that. Not roughly. Exactly. It's one of the truest numbers we have. So they sent the beam to Venus, and it struck the planet, and a faint echo came bouncing back, like a shout returning off a distant cliff. And they timed it. They timed how long the round trip took, out and back, with a good clock. And because they knew precisely how fast the beam had travelled the whole way, that little stretch of time told them, directly, in honest kilometres, exactly how far away Venus was at that moment. And from that, at last, they nailed down the astronomical unit, the true length of the ruler. And you know what that number is, now that we have it? The astronomical unit is fixed at 149,597,870,700 meters. Say it slow, 149,597,870,700 meters. That's the distance from here to the sun. That's the width of the footing the whole cosmos stands on. And here's what makes that radar bounce so special, so different from every clever trick above it on the ladder. This is the only rung, the only one, that we measure with a real physical clock and an actual beam of light we sent out ourselves. Everything higher up is inference, deduction, borrowing, but this rung? This one we touched. We reached out a hand of radio light and felt the distance to another planet, the way you'd feel for a wall in a dark room. It's the bedrock, it's the one honest, absolute, measured in meters, step that the entire towering rest of it leans on. And we didn't stop with Venus, either. There's one more measurement down here at the bottom that I have to tell you about, because it's just so lovely and so exact it makes me smile. It's the distance to the moon. Now, back in 1969, when the first astronauts walked on the moon, they left something behind. Not just footprints and a flag. They set out little mirrors, special mirrors called retroreflectors. The clever thing about them is that they bounce light straight back the way it came, no matter what angle it hits them, the same way the eyes of a cat or a road sign flare back at your headlights. The astronauts set these mirrors down on the grey dust and left them facing the sky. And the Soviet moon rovers, the lunokhds, carried mirrors up there too. And so ever since, from that day in 1969 right up to now, we've been able to shine a laser, a tight, pure beam of light, up from the Earth, across all that empty black, hit one of those little mirrors sitting up there on the moon, and catch the flash of it coming back. Lunar laser ranging, we call it. And by timing that beam, out and back. The same trick as the radar, but with visible light and a mirror we placed ourselves, we can measure the distance to the moon down to the millimetre. To the millimetre. 250,000 miles away, roughly, and we know where it is to less than the width of a fingernail. We can watch the moon drift slowly away from us, a few centimeters a year, just by the patient bouncing of light off a mirror an astronaut set down with his glove. I think about that sometimes, on a clear night, looking up, that there are little mirrors up there sitting in the dust, and every so often a thread of laser light reaches up and touches them and comes home. We can literally measure the distance to the moon by bouncing a light off it. Not guess, not estimate, measure. There's something so tender about it to me, this reaching out across the void with a beam of light just to know exactly how far away our nearest companion floats. So there we are. That's the bottom of the ladder, all laid out. The ground floor. The size of the Earth from a shadow, thanks to Eratosthenes. The distance to the moon from an eclipse, thanks to old Hipparchus. And now down to the millimetre with our lasers and our mirrors, and most important of all, the distance to the Sun, the great astronomical unit, that 149 billion metre ruler, measured at last, cleanly and directly, by bouncing radar off Venus back in 1961. These are the rungs we can stand on solidly. These are the ones anchored to real, physical, out and back measurements. Light we sent, echoes we caught, clocks we trusted. But you see the trouble, don't you? Even half asleep, I think you can feel where this is heading. The Sun is 8 light minutes away, and we can reach it with radar. The Moon, a light second and a bit, and we can reach it with a laser. But the stars? The nearest star to our own Sun is not 8 minutes away. It's more than 4 years away at the speed of light. You cannot bounce a radar beam off a star and wait 4 years for a whisper of an echo that would be far too faint to ever hear. The trick that got us this far, send a beam, catch the echo, simply runs out. It can't reach. The rung crumbles away beneath your foot the moment you try to step past the edge of our own little solar system. And that's the heart of the whole story I want to tell you tonight, the secret I promised you at the start. Every single rung on this ladder can only carry you so far before it gives out. And when it gives out, you can't just leap. You have to invent a whole new trick, a new rung, and here's the crucial, delicate, almost frightening part. You have to build that new rung by standing on the old one. You calibrate the new trick using the distances you already measured with the trick below it. You take out a loan against the rung beneath your feet. Parallax will borrow from radar, and the next trick will borrow from parallax, and the one after that will borrow from that, all the way up. Every distance in the heavens to the farthest exploding star at the very edge of the visible is inherited, handed down, borrowed from the rung below, and the whole magnificent tower traces all the way back down to that one radar echo from Venus, and the width of Earth's orbit, a gap that light crosses in about 8 minutes. Now hold that thought gently, because it's going to matter more than you know. If every distance is borrowed from the rung below it, then what in the world happens if one of those rungs, somewhere down low, turns out to be wrong? Just a little wrong. A quiet, hidden mistake nobody noticed. What happens to everything stacked on top of it? Keep that question loose in the back of your mind as you drift. We'll come back to it. Because it isn't a hypothetical. It has already happened, once, in a big way, a single mistake that made the whole universe suddenly twice as large as everyone thought. But that's a story for a little later up the climb. For now, let's take the first real step off the solid ground and out toward the stars. Let's talk about how anyone, standing on a spinning rock, could possibly measure the distance to a star that's 4 years away at the speed of light. And to understand it, you don't need any equipment at all. You've already got the whole instrument built into your own face. Hold up one finger in front of your nose, arm's length out in front of you. Now, close one eye. Just look at your finger with the other. Now switch. Close that eye, open the first. Back and forth, one eye then the other. And watch what your finger does against the far wall behind it. It jumps, it hops back and forth against the background, side to side, even though you're holding it perfectly still. Your finger didn't move, your eyes did. You're looking at the same finger from two slightly different spots, the two positions of your two eyes a couple of inches apart. And that little difference in viewpoint makes the near thing appear to shift against the far things. That little hop has a name. It's called parallax. And it is one of the most powerful ideas in the whole history of measuring the sky. Because here's the leap. Bring your finger closer to your face and do the blink again. The hop gets bigger. Push your finger farther away, arm fully out, and blink again. The hop gets smaller. The farther away the thing is, the smaller its little jump. And that means, if you can measure the size of the jump precisely enough, you can work backward and figure out exactly how far away the thing is. Small hop, far away. Big hop, close. The shift itself is the ruler. Now the stars are terribly, terribly far, so their hop is going to be minuscule, and the width between our two eyes is nowhere near enough of a difference to make a star budge. So the astronomers reached for the biggest pair of eyes they could possibly find. And what's the biggest gap we've got available to us, sitting here on the Earth? It's the Earth's own orbit. Because we don't sit still. We ride this planet all the way around the sun once a year in a great slow circle. So if you look at a nearby star tonight, and then you wait 6 months, half a year, until the Earth has swung all the way around to the far side of its orbit, you are now looking at that same star from a spot hundreds of millions of kilometers away from where you stood before. 2 viewpoints. But instead of 2 inches apart, they're 2 full astronomical units apart, the whole width of our orbit that baseline light crosses in about 16 minutes end to end. That's the widest pair of eyes we could ever hope to blink. And you look at the nearby star from one side of the orbit, and then from the other. And you measure its tiny little hop against the distant background stars, the ones so far away they don't budge at all, and from the size of that hop, you get the distance. That's it. That's the whole trick. That's how you measure a star. You use the whole Earth's yearly journey as the blink between 2 eyes, and you catch the faint, faint shift of a star against the deeper dark behind it. And I do mean faint. This is why it took so heartbreakingly long to actually pull off. You would think, with a baseline that huge, the entire width of our orbit, the stars would swing about generously. But they are so far away that even from opposite ends of our orbit, the nearest star of all shifts by only the tiniest sliver of an angle. How tiny? Well, the very nearest star system to our Sun, called Alpha Centauri, shifts by only about 3/4 of 1 arcsecond. And I should tell you what an arcsecond is, because it's how we measure these little hops. If you take the whole dome of the sky and slice it up finely, an arcsecond is one tiny 60 by 60 division of a single degree. It is a hair. It is nothing. 3/4 of an arcsecond, the shift of our very nearest neighbour, is about the width of a small coin seen from several kilometres away. Picture that. A coin laid flat, and you back away from it. Down the street, out of the neighbourhood, kilometres off, until it's just the faintest speck. That's how much the closest star moves. And the farther stars move even less than that. So you can see the mountain they had to climb. To measure a star's distance by parallax, you have to catch a shift smaller than a coin seen from kilometers off, against a sky that's shimmering and blurring through the whole thick, restless ocean of our atmosphere. For centuries, the best astronomers in the world tried and failed. They knew the trick was sound. It was just the blink test, the same one your own two eyes do 1,000 times a day. But the shift was simply too small for their instruments to catch. Try after try, generation after generation, they aimed their telescopes at the brightest, nearest-looking stars, hoping to see them wobble across the year, and the wobble hid just below what they could measure. The idea was right. The tools weren't ready yet. And so the stars kept their distances secret, year after year after year, refusing to give up that one tiny telltale hop. And that's where I'll leave us for tonight's first little while. Right on the edge of the moment, somebody finally caught it. Right at the foot of that first great step off solid ground and out among the stars, with the whole clever trick understood and the shift still just barely, maddeningly out of reach. Somebody's about to succeed. Somebody, in the year 1838, is about to become the first human being in all of history to measure the true distance to a star. But he's going to have to wait a moment, and so will we, because you're drifting now, I can tell, and there's no rush at all. The stars have kept their secret for thousands of years. They can keep it a few minutes more while you settle deeper into that pillow. So, Friedrich Bessel. He was 44 years old in 1838, a German mathematician and astronomer working at the Königsberg Observatory in what is now northeastern Poland, and he had spent the better part of his adult life making precise measurements of the sky. Not glamorous work, mostly, not the sort of thing that fills the newspapers. It was meticulous, painstaking, almost monastic work. Measuring and remeasuring the positions of stars, cataloguing their tiny drifts and wobbles, building up tables of numbers with the patience of someone who genuinely believed that the numbers were trying to tell him something worth hearing. And he was right about that. Bessel did not pick the most famous star, or the brightest star, or the star most people were watching. He picked 61 Cygni. It's a star, actually a pair of stars orbiting each other, in the constellation Cygnus the Swan, and it had attracted his attention for an interesting reason. 61 Cygni moves. Not toward us or away from us, but sideways across the sky, drifting slowly relative to the stars around it, and that sideways drift, called proper motion, suggested to Bessel that it might be relatively close. A distant star moves almost imperceptibly across the centuries. A nearby one might actually crawl, just a little, against the backdrop of its far more distant neighbours. 61 Cygni had been noticed and named the flying star because of that drift, and Bessel thought that a flying star might be a nearby star, and a nearby star might just show a measurable parallax. He was right about that too. For months through the second half of 1837 and into 1838, Bessel pointed his heliometer, a specialized telescope fitted with a split lens that allowed him to measure tiny angles between stars with exceptional care at 61 Cygni and at two other stars nearby that served as his reference points. The reference stars had to be stars he was confident were genuinely far away. So far that they wouldn't shift at all compared to what he was watching. They were his fixed backdrop, his two eyes in a sense. And between those fixed points and the dancing little dot of 61 Cygni, he was looking for the hop. The hop was there. Over the course of a full year, as the Earth swung from one side of its orbit to the other, carrying Bessel and his telescope and his heliometer and all of Königsberg with it through that huge arc of 300 million kilometers, 61 Cygni shifted back and forth against its background, like a fingertip held at arm's length, shifting left and right as you blink each eye in turn. The total shift was about 0.628 arcseconds across. Half of that, measured from one side of the orbit to the other, gave a parallax of roughly 0.314 arcseconds. Now, an arcsecond is 1/3600th of a degree. It is a vanishingly small angle. Imagine a single coin, a penny, say, sitting on a surface. Walk away from it. Keep walking. Walk until you are somewhere between 3 and 4 kilometers away. At that distance, if you could still somehow see the penny at all, it would subtend just about 1 arcsecond in your field of view. That is the apparent size, the angular width, of something about 2 centimeters across seen from 3.5 kilometers away. And Bessel was measuring a shift roughly a third that size. He was measuring the hop of 61 Cygni with enough precision to catch a movement smaller than the apparent width of a penny seen from 10 kilometers off. And from that measurement, from that tiny, painstakingly one angle, he worked out the distance. It came to about 10.4 light-years. The actual modern value is about 11.4 light-years. He was within 10% of the truth, using instruments built in the early 19th century, measuring an angle so small that no one before him had managed to catch it at all. That is not a small achievement. That is a staggering one. And with it, for the first time in the whole long history of human beings looking up at the night sky and wondering how far away the stars were, someone had an answer, a real answer, a number with actual kilometers attached to it. Not a guess, not a philosophical argument, not a calculation built on other calculations, a direct geometric measurement, the same basic trick as 2 eyes giving you depth perception, scaled up to the Earth's orbit. He published his results in 1838, and the astronomical community received them with a mixture of delight and slightly wounded pride, because it turned out that 2 other astronomers had been working on the same problem at almost exactly the same time. Thomas Henderson, a Scottish astronomer, had observed Alpha Centauri from the Royal Observatory at the Cape of Good Hope in South Africa. Because Alpha Centauri is a southern sky star, and you can only properly see it from southern latitudes. He had actually made his observations before Bessel did, but he had been hesitant to publish. The shift seemed almost too large to believe, and he didn't want to look foolish. When Bessel's paper appeared, Henderson quickly submitted his own results. Alpha Centauri's parallax came out to about 0.75 arcseconds, larger than 61 Cygni's, which means Alpha Centauri is closer, which it is. It's our nearest stellar neighbour, the closest star system to our Sun, at about 4.2 light-years. And at nearly the same time again, Wilhelm Struve in Russia reported a parallax measurement for Vega, one of the brightest stars in the summer sky. 3 measurements, 3 different stars, 3 different observatories, almost simultaneous. The age of stellar distances had arrived, all at once, from 3 directions. After thousands of years of staring at the stars and knowing nothing about how far away they were, humanity cracked the problem in what amounted to a single season. There's something about that I find quietly wonderful, lying here in the dark and thinking about it. These 3 men, Bessel in Nigsburg, Henderson at the Cape, Struve in Dorpat, didn't know each other was so close to the same finish line. They were each working in their own cold observatory, squinting at their own instruments, nursing their own private excitement about their own particular star. And yet they all arrived at the door at nearly the same moment. The world was ready for the answer, and the answer came from 3 places at once. Out of Bessel's measurement and the measurements that followed, a new unit was born. Astronomers realized they needed a natural way to describe stellar distances, one that encoded the method itself, the parallax trick that had won them the measurement. And so they defined the parsec. A parsec is the distance at which a star would show a parallax of exactly 1 arcsecond. At that distance, the apparent shift from one side of Earth's orbit to the other would be a single arcsecond wide. No star is actually that close. The nearest ones are still several arcseconds below that threshold, but the parsec makes the math tidy. 1 parsec works out to about 3.26 light years, or, if you prefer actual kilometers, something in the neighborhood of 3.086 times 10 to the 13th. 30 trillion kilometers, give or take. The word itself is a little contraction, parallax plus arcsecond, folded together into one syllable, parsec. The unit carries the method inside it, the way a good tool's name sometimes tells you exactly what it does. Bessel's star, 61 Cygni, sits a bit more than 3 parsecs away. Alpha Centauri is about 1.3 parsecs, Vega is about 8 parsecs. And now, with a method and a unit, astronomers could set to work measuring everything in the sky that was close enough to show a parallax shift. But here is where the first wall appears. Because close enough is the crucial phrase there, and it is a rather frustrating limitation. The problem is the atmosphere. Our thick, restless, turbulent blanket of air is wonderful for keeping us alive and rather terrible for making precise astronomical measurements. Even on the clearest nights, the air shimmers and blurs. Starlight doesn't come in perfectly still, it wavers and dances a little, smeared by pockets of warm and cool air sliding past each other all the way up through the troposphere and beyond. This shimmering is what makes stars twinkle, which is pretty, but it also sets a hard limit on how precisely you can measure a star's position from the ground. It's like trying to measure the exact position of a coin at the bottom of a gently rippled swimming pool. You can get close. You can get quite close. But the ripples themselves impose a limit on your precision. For stellar parallax, this matters enormously. Ground-based telescopes, working through Earth's atmosphere, can measure parallax angles down to about a few thousandths of an arcsecond, a few milliarcseconds, on a good night, with careful work and a lot of averaging. That precision fades to uselessness for stars more than a few hundred light-years away. Roughly 100 parsecs, about 326 light-years, is about the practical ceiling for ground-based parallax. Beyond that, the shifts become smaller than the noise, smaller than the shimmer, smaller than what the ground can reliably catch. And 100 parsecs, while it sounds like an enormous distance, is a very small neighborhood in a galaxy that is roughly 30,000 parsecs across. So after the triumph of the 1838 measurements, after the joy of finally reaching the first rung, astronomers found themselves looking up at a ladder that extended far above them into the dark, and most of it was still out of reach. The atmospheric ceiling was real. The rung they'd climbed was the right one, the solid one, the geometric one. The one that didn't require any assumptions about the stars themselves, but it only reached so far, and the universe was so much bigger than 100 parsecs. The way past the ceiling was to go above it. This is where I always feel something quietly triumphant when I think about it, this moment when human beings, having run into a physical limit they couldn't engineer their way around on the ground, simply decided to put the telescope in space. In 1989, the European Space Agency launched a satellite called Hipparcos. The name is both an acronym, High Precision Parallax Collecting Satellite, and a deliberate nod to Hipparchus, the ancient Greek astronomer who had done so much to map the sky more than 2,000 years before. Hipparchus left Earth's atmosphere entirely behind and spent nearly 4 years, from 1989 to 1993, measuring the positions and parallaxes of stars with a precision that no ground telescope could match. It measured the parallaxes of about 118,000 stars, most of them to a precision of about a milliarcsecond or better. That was a transformation. Not a modest improvement, but a leap of an order of magnitude in the precision and the number of stars measured. The catalogue that came out of Hipparchus became the bedrock of stellar distances for decades. But even Hipparchus, for all its achievements, was just the beginning of what was possible once you got above the air. On the 19th of December 2013, and I like that we have an exact date for this, because it feels like something that deserves a date, the European Space Agency launched Gaia. Gaia is a spacecraft, and its only job is to stare at stars. It orbits at a point called L2, about 1.5 million kilometers from Earth in the direction away from the Sun, where the gravity of the Sun and Earth and the spacecraft's own orbital motion all balance in a useful way. It sweeps its 2 telescopes slowly around the sky, measuring the positions of stars over and over and over again as Earth and Gaia slowly orbit the Sun, watching each star shift back and forth against the background with a precision that would have seemed like fantasy to Friedrich Bessel. Gaia measures parallaxes to an accuracy of about 20 to 30 microarcseconds for the brightest stars. A microarcsecond is 1/1,000,000th of 1 arcsecond. It is the apparent size of a human hair seen from about 10,000 kilometers away. Gaia is catching shifts that small for billions of stars, building up an exquisite 3-dimensional map of our galaxy with a thoroughness and precision that simply has no historical precedent. As of the mid-2020s, Gaia has measured reliable parallaxes, reliable distances, for something in the neighborhood of 2 billion stars. Not 118,000. 2 billion. It has pushed the reach of direct geometric parallax out to tens of thousands of light-years, deep into the structure of the Milky Way, and it has done so with enough precision that it is right now, as we drift through this quiet night together, recalibrating every single rung above it. Every method that was anchored to stellar parallax is being updated, revised, and tightened by what Gaia keeps finding. The foundation stone is getting firmer all the time. And yet, even Gaia has its limits. Even Gaia's extraordinary micro-arcsecond precision fades to noise when you point it at a star in another galaxy. Andromeda, our nearest large galactic neighbor, is about 2.5 million light-years away, roughly 770,000 parsecs. The parallax shift of a star in Andromeda, as seen from Earth's orbit, would be on the order of 1/1,000,000th of a microarcsecond. That is not a measurement any instrument built from matter and energy is ever likely to make. It is so small it bumps up against the kind of numbers that stop meaning anything physical. So the relay race has to continue. Parallax, the geometric rung, the bedrock rung, the one that needs no assumptions about what the stars are doing, only careful observation of where they appear to be, carries the baton as far as it can. Tens of thousands of light-years across a good slice of our own galaxy. And then it reaches the edge of its own strength and has to hand off. The question the next rung has to answer is, now that you can't measure the distance directly, how do you measure it at all? The answer is something that sounds almost too simple when you first hear it. almost like cheating. And then you think about it for a moment, in the quiet of a night like this one, and you realize it's not simple at all. It's genuinely clever. It's one of those ideas that required someone to sit very still and think very carefully about what light is actually doing on its way across space. The idea is this: if you know how bright something truly is, not how bright it appears, but how bright it actually is, in absolute terms, in real watts of energy pouring out in all directions, then the dimmer it looks to you, the farther away it must be. Because light thins out as it spreads. A light bulb seen from a meter away is brilliant. The same bulb seen from 10 meters away is much dimmer. From 100 meters it is dimmer still. And the rule that governs this thinning is one of the most fundamental in all of physics. It's called the inverse square law, and it says simply that if you double the distance, you get 1/4 the brightness. Triple the distance, 1/9. The brightness falls off as the square of the distance every time with perfect mathematical regularity. So if you know the true brightness of the bulb and you measure how bright it appears from where you're standing, those two numbers together give you the distance. You don't need a tape measure. You don't need a radar echo. You just need to know the wattage of the bulb and then measure how dim it looks from your position, and the inverse square law does the rest. The problem, of course, is knowing the wattage. How do you know how truly bright a distant star is? A star sitting in another galaxy might look quite faint, but is that because it's genuinely a dim star, or because it's an enormously brilliant one, but just very far away? Without some independent way to know the true luminosity, the distance is undetermined. The brightness you measure could mean a dim star nearby or a dazzling star far off. You can't tell them apart from the apparent brightness alone. What astronomers needed was a class of objects whose true luminosity they could figure out independently, not from the distance, but from some other property of the object itself. Some property they could measure directly, without already knowing the distance. If they could find that, a kind of cosmic object whose wattage was written on the object itself, readable from any distance, they could use it to climb far beyond parallax's reach. They called such an object a standard candle. And finding the first reliable one, the one that would ultimately let human beings measure distances to other galaxies, settle a great debate about the size of the universe, and eventually reveal the most unexpected thing anyone had ever discovered about the cosmos, required a woman sitting at a desk in Cambridge, Massachusetts, peering at glass photographic plates through a magnifying loupe, measuring and recording and noting and thinking, night after quiet night, on 30 cents an hour. And that story is the one that's waiting for us just a little further along. But I want you to sit with this rung for a moment first, the parallax rung, before we climb. Think about what it means. Every single distance in the universe that's larger than our solar system starts here. It starts with a triangle. It starts with a baseline, the diameter of Earth's orbit, 300 million kilometers wide, which light covers in about 8 minutes, and an angle so small that the atmosphere itself hides it. The nearest star to the Sun is about 4.2 light-years away. 4.2 light-years, that is roughly 40 trillion kilometers. And yet the way we know that, the ultimate bedrock measurement underneath every extragalactic distance we've ever made, is a parallax shift of 3/4 of an arcsecond. A shift smaller than the width of a coin seen from several kilometers away. Everything above this rung is borrowed from that. Every galaxy distance, every statement about the size of the observable universe, every claim about how far away any object in the cosmos might be, All of it traces back, through a chain of calibrations, to this one geometric measurement, to the blinking eye trick with Earth's orbit as the two eyes. The whole vast scaffolding of our knowledge of the universe rests on a triangle, a very small triangle with a very short base, but a real one, a measurable one. A triangle made not of assumptions, but of geometry. And here is the thing that I find gives me a particular quiet feeling when I let myself really sit with it. Before Bessel measured 61 Cygni in 1838, nobody had a single confirmed distance to any star. The sky was a dome of unknown depth, beautiful and bewildering, full of objects that might have been a few light years away or a few million, and there was no reliable way to say. The stars kept their distances the way the deep ocean keeps its secrets, with simple, impenetrable depth. After Bessel, after that one winter of careful measurement in Nigsburg, we had 3 of them. 3 stars with real distances attached. And then more, and more, and more. Hipparchos, Gaia, 2 billion. We went from 0 to 2 billion in about 185 years, and every one of those distances is ultimately the same trick, the same blink test, the same triangle. The night is getting a little later now, and I can hear in the rhythm of things that some of you have already drifted a little. That's perfectly fine. The stars aren't going anywhere. 61 Cygni is still out there in Cygnus, still flying slowly across the sky on its own private drift, still sitting about 11.4 light-years away, patient as anything. It doesn't mind if you're asleep, the measurement stands whether you're following it or not. But for those of you still with me, still lying there in the warm and the dark with one small part of your mind still curious, let me walk you toward the next step. Because parallax has now done everything it can for us. It's measured our solar neighborhood beautifully, thoroughly, with Gaia's 2 billion points of light mapped into 3 dimensions like a great luminous cloud around us. It's given us the gold standard distances that everything else will be calibrated against. And now it's reached its edge. Its precision runs out before we get anywhere near the galaxies beyond our own. And the universe is not one galaxy. The universe is, well, we'll get to how big it really is, but it's bigger than one galaxy by an almost inconceivable factor. So the baton gets passed. Parallax hands it off to the next runner. And the next runner is someone whose true luminosity you can figure out just by watching it pulse. Think about what I said a moment ago. A standard candle is any object whose true brightness you know independently, whose wattage is readable from the object itself without needing the distance. And now imagine that someone found a particular type of star that breathes. A star that swells and shrinks on a clockwork rhythm like a slow, steady heartbeat, expanding and contracting over days or weeks in a perfectly regular cycle. And imagine that when you plot those stars on a chart, brighter ones on one side, dimmer ones on the other, you find something extraordinary. The brighter ones pulse more slowly, the dimmer ones pulse faster. There is a precise, reliable, measurable relationship between how fast a star of this type beats and how bright it truly is. That would mean you could look at any such star, anywhere in the sky, and simply time its pulse. Count the days between peaks of brightness. And from that one number, the period, the heartbeat interval, you could read off its true luminosity as though you were reading a label on the side of the bulb. And then, with the true luminosity known, you'd measure how bright it appears and let the inverse square law give you the distance. That would be a standard candle of extraordinary power. Precise, reliable, usable from millions of light years away. A way to carry the ladder from our own galaxy to others, from the known to the unknown, from Bessel's triangle to the far shore of the cosmos. And that star exists. It's called a Cepheid variable. And the relationship between its period and its luminosity, the precise, remarkable, universe-spanning law that turned it into humanity's first extragalactic ruler, was discovered in the first decade of the 20th century by a woman who was not supposed to be doing research at all, who was paid less than factory workers for her careful and transformative labour, and whose name deserves to be as familiar to us as any in the history of science. Her name was Henrietta Swan Leavitt. She worked at the Harvard College Observatory, but she worked there as what the institution called a computer. Not a machine, a person. A woman hired to do the painstaking calculation work that the observatory's male astronomers preferred not to spend their time on. The computers, as they were called, examined photographic glass plates, images of the sky, recorded on large flat sheets of treated glass, and they measured things. They measured stellar positions, brightness levels, the tiny differences between how a star looked on one plate and how it looked on another. It was meticulous, quiet, repetitive work. Important work, but not the kind of work that was supposed to lead anywhere extraordinary. Leavitt was assigned to study a particular kind of variable star, stars that changed in brightness over time, and she focused especially on stars in a region of the sky called the Small Magellanic Cloud, a small companion galaxy visible from the southern hemisphere, hovering near our own Milky Way like a pale smudge of light. She worked between about 1908 and 1912, examining plate after plate, tracking which stars got brighter and which got dimmer and how long each cycle took. And she noticed something. The brighter Cepheids in the Small Magellanic Cloud took longer to pulse. The fainter ones pulsed faster. And not just roughly, precisely. The relationship was a clean mathematical line on a chart, and it held up across every Cepheid she could measure in that cloud. This was the period-luminosity relation. Today it's called Leavitt's law. She published her findings in 1912, and the reason those findings were so powerful, the reason they became the key that unlocked extragalactic distance, is something worth pausing on. The Small Magellanic Cloud sits at a vast distance from us, but all the stars in it sit at very nearly the same distance. It's a cloud, a cluster, and it's so far away that the difference between one side and the other is negligible compared to the whole distance. So when Leavitt compared the apparent brightnesses of Cepheids in the Small Magellanic Cloud, she was making a fair comparison. The brighter-looking ones were genuinely more luminous. They weren't just closer to her. They were all at essentially the same distance, and the genuinely more luminous ones pulsed more slowly. The mechanism behind this, which was worked out afterward, involves a layer of doubly ionized helium deep in the star's atmosphere. In its ionized state, this layer becomes more opaque when compressed. It traps heat rather than letting it through, which causes the star to expand outward. As it expands, the layer cools, becomes more transparent, releases the heat, and the star contracts under its own gravity again. It's a valve, a natural engine, running on the physics of how helium behaves when you squeeze it. Astronomers called it the Kappa mechanism, and Arthur Eddington had worked toward understanding it. The bigger and more luminous the star, the longer this breathing cycle takes. The smaller and fainter, the quicker. The period is tied to the size, and the size is tied to the luminosity, and so the period is tied to the luminosity with a precision that you can rely on. And so Leavitt's chart was not just an interesting pattern, it was a key. Time the pulse of any Cepheid anywhere in the universe, and you know its true luminosity. And knowing its true luminosity and measuring its apparent brightness gives you the distance. The relay baton had been fashioned. All that remained was someone to run with it. The prototype of this class of stars, by the way, is Delta Cepheid, a star in the constellation Cepheus, the King, which is why the whole class is called Cepheids. You can actually see it with the naked eye from a dark sky location, brightening and dimming over a period of about 5.5 days, in a rhythm so regular you could set a clock by it. And here is something I find quietly charming, the North Star, Polaris, that fixed and faithful point that all the other stars seem to wheel around, that sailors and wanderers have navigated by for millennia. Polaris is itself a Cepheid. A faint one, varying only slightly over a period of about 4 days, but a Cepheid nonetheless. The very star that people have used to find their bearings on Earth for thousands of years is, in its own subtle way, breathing. Henrietta Leavitt was paid about 30 cents an hour for the work that produced this discovery. She was not encouraged to pursue her own research directions. The observatory's male astronomers set her agenda. When the Swedish mathematician Gösta Mittag-Leffler attempted, in 1925, to put her name forward for consideration for a Nobel Prize, having heard of her period-luminosity law and its enormous importance, he was informed that Leavitt had died of cancer in 1921. 4 years earlier. Nobels are not awarded posthumously. She never received the prize that her law arguably deserved more than several that were awarded in those years. And for a long time, her name was not nearly as well known as it should have been. That's beginning to change. It deserves to change more. What Leavitt found on those glass plates, in that quiet institutional role that was supposed to keep her from doing anything consequential, turned out to be one of the most consequential discoveries in the history of human knowledge. It is the reason we can talk at all about distances to other galaxies. Everything above this rung of the ladder stands on what she found. Now, the night is still soft around you, and you are perhaps beginning to feel the gentle pull of sleep in a new way. The kind that comes not from exhaustion, but from the slow, comfortable feeling of having learned something real and let it settle into you. The ladder has 2 rungs under our feet now. The geometric bedrock of parallax, stretching tens of thousands of light years with Gaia's 2 billion measured stars, and just above it, this new rung being built from the pulse of variable stars. From the breathing helium valve and the clockwork rhythm that Leavitt mapped onto her glass plates in the early 1900s. The next question, the one that's sitting quietly at the back of your mind, even as you drift, is where exactly Leavitt's law was first used to actually measure an extragalactic distance, where someone actually took this key and turned it in a real lock and opened a door onto a bigger universe than anyone had imagined. That story involves a man named Edwin Hubble and a long-running argument about whether the Milky Way was the whole universe or just one small piece of something vastly larger, and a faint spiral smudge of light in the constellation Andromeda that people had been looking at and arguing about for years without being able to settle the question one way or the other. But that's the next step on the climb, and it comes with its own beauty and its own surprise and its own crack, a fault line that, when it was finally found, would shift the entire scale of the known universe overnight. No rush to get there. We've come a good way tonight already. You know how the ladder is built, you know the bedrock it stands on, you know the tool Leavitt gave us, and what it cost her. The Andromeda question is just up ahead, around a quiet corner, waiting patiently in the dark, the same way the stars always wait, with absolute, unhurried confidence that they will still be there when you're ready. And if you're not ready, if you've drifted now, if the pillow has won, that is exactly right. That is what the night is for. Leavitt's law will still be true when you wake up. The Cepheids will still be breathing. The parsecs will still be waiting, each one 3.26 light-years long, stacked like quiet steps in a staircase leading off into the dark. Farther than you can see from where you're lying right now, farther than Bessel could have dreamed, farther even than Gaia can quite reach, but not farther than we can measure. Not anymore. And how we learned to reach the rest, that part of the story is still ahead. So, before we step into Andromeda, before we get to Hubble and the great debate and the number that changed everything, there's a layer of the Cepheid story we haven't quite opened yet. A question sitting underneath Leavitt's discovery that deserves a slow, careful moment of its own. You already know what she found. A Cepheid's pulsation period tells you its true brightness. A slow pulse means a luminous star. A fast pulse means a dimmer one. Measure the period, apply Leavitt's law, compare to the apparent brightness, and the inverse square law gives you the distance. You know what it cost her to find this: 30 cents an hour, photographic plates, a department that decided what she was permitted to study, a Nobel Prize that came too late because she had already died by the time a nomination was attempted. But here's the question underneath all of that. Why does the pulsation period tell you anything about the star's true brightness? Why should those two things be connected at all? It sounds, on the surface, too convenient. A star happens to blink at a speed that reveals how luminous it is. If that were just a coincidence, an interesting correlation with no underlying cause, you'd be right to distrust everything built on top of it. And everything above the Cepheid rung would be resting on luck. It isn't a coincidence, it's a physical mechanism. And once you have a picture of it, the whole thing settles into place the way a key settles into a lock. Deep inside a Cepheid, at a particular depth somewhere in the outer layers, not the scorching core, but a shell sitting a good portion of the way from the surface inward, there is a layer of helium. Not ordinary helium, the quiet inert gas you'd fill a birthday balloon with. This is doubly ionized helium. Helium that has had both of its electrons stripped away by the intense heat of the star's interior, leaving just the bare nucleus, exposed, reactive, and very sensitive to what's happening around it. And this layer behaves in an unusual, self-reinforcing way. When the star contracts inward, when gravity momentarily wins the tug-of-war with the pressure pushing outward from the core, this shell of doubly ionized helium gets compressed. And as it compresses, it becomes more opaque, more resistant to the radiation trying to pass through it and escape from the interior. The light and heat from the core get blocked. They accumulate below the shell, the way heat accumulates in a room when you close all the windows. The pressure builds, and eventually the pressure wins, the star pushes back out. Now the outer layers are expanding. The shell of ionized helium stretches and cools. As it cools and thins, it becomes transparent again. The trapped energy floods outward in a rush. The star brightens sharply. This is the peak of its light curve, the brightest moment of the cycle, the flash that the observer far away can measure. Then the heat is gone, the pressure drops, gravity reasserts itself, the layers fall back in, and the whole cycle begins again. This is the Kappa mechanism. It's sometimes called the Eddington valve. The valve image is the apt one, a valve opening and closing deep inside the star, releasing and trapping energy on a schedule driven by the particular physics of that one layer of doubly ionized helium. Not random, not chaotic. Clockwork. Now, why does the speed of that clock tell you the star's luminosity? Because the speed of the clock depends on the size of the machine. A larger, more massive, more luminous star has a deeper, more expansive system, more star to compress and re-expand, a grander cycle to complete. It breathes slowly. And a larger, more massive star is also brighter, because a larger star burning at stellar temperatures pours out more energy per second. So the slow pulsing stars and the bright stars are the same stars described from two different angles. The period is a measure of the size. The size determines the luminosity. When Leavitt noticed in those photographic plates from the small Magellanic Cloud that the slow Cepheids were the bright ones and the fast ones were the dimmer ones, she was reading the Kappa mechanism written out in the light curves of 100 distant stars, though she didn't have that name for it. She had the law before anyone had worked out the full theory. She read a physical truth off glass plates at 30 cents an hour, and the physical truth turned out to be more lasting than most of what the institution around her was doing. Now about these stars themselves. Cepheids are not modest or subtle objects. They are luminous supergiants among the most brilliantly lit stars in any galaxy. Many of them pour out thousands of times the light of our sun, some of them tens of thousands of times brighter. They swell and contract over cycles of days to weeks, and the variation in brightness is real enough to track carefully from a moderate telescope if you know where to look and what you're watching for. The star that gave the whole class its name is Delta Cephei, in the northern constellation Cepheus, not far in the sky from the North Star. It varies on a cycle of just over 5 days, brightening, dimming, brightening again, as regular as anything in the sky, and it's been doing this for longer than anyone has been watching. It's the prototype, the standard, the one after which every Cepheid is named. And then there is Polaris, the North Star itself, the one the entire northern sky appears to rotate around, the one associated for centuries with constancy and fixed orientation, the one sailors have steered by in the dark for as long as people have been sailing. Polaris is itself a Cepheid, a mild one, pulsating with only small changes in brightness, changes modest enough that they went unnoticed for a long time. But real. It has a period. It runs the Kappa mechanism, just like any other Cepheid. The star people chose as the symbol of the unchanging is quietly and continuously breathing, contracting and expanding on its schedule, while everyone below was busy navigating by it. There's something worth sitting with in that. But what matters for the distance ladder is not the Cepheids in our own galaxy, dramatic as they are. What matters is that they are bright enough, those thousands or tens of thousands of solar luminosities, to be spotted in other galaxies entirely. This is the great leap that Leavitt's law made possible. Bessel's parallax method could reach the nearest few hundred parsecs before the angular shifts became too small to measure reliably. Hipparchus extended that. Gaia extended it further still, to micro-arcsecond precision, to millions of measured parallaxes. But even Gaia cannot measure parallax across intergalactic distances. The gap between galaxies is too enormous. The shift of a star in Andromeda against the background of more distant objects would be smaller than anything any instrument has yet been able to resolve. The geometric rung runs out of reach, and it runs out far short of the nearest galaxies. but a Cepheid burning tens of thousands of times more brightly than the Sun can be identified from millions of light-years away with a sufficiently large telescope. Find one. Watch its brightness change over days or weeks. Measure the period. Read off the true luminosity from Leavitt's law. Compare that to the apparent brightness. Apply the inverse square law. Out comes the distance. One pulsing star. One number. Millions of light-years. The question was whether anyone had the telescope, the patience, and the sky time to actually do it. Enter Edwin Hubble. The question Hubble was working toward, the question the entire astronomical community had been arguing over, was about the largest possible scale, about whether the Milky Way was the entire universe or just one piece of something enormously, perhaps unimaginably, larger. By 1920, this had crystallized into a formal public dispute between two prominent positions. On one side, Harlow Shapley, who believed the mysterious spiral nebulae, those faint, soft smudges scattered across photographic plates, some spiral in shape, some elliptical, were nearby objects within or near the Milky Way itself. Clouds of gas, perhaps, or smaller systems of stars, but nothing outside our own galaxy. On the other, Heber Curtis, who argued they were independent systems, separate galaxies each comparable in scale to the Milky Way, separated from us by distances of millions of light-years. He called them island universes, each one a continent of stars, floating in the void, unreachably remote. In 1920, the two men debated the question before an audience at the National Academy of Sciences, the Shapley-Curtis Great Debate, it's now called. And the evidence at the time was genuinely ambiguous. Each position had arguments, neither had proof. The audience left without a verdict, because the data couldn't deliver one yet. What would settle it was a single real measurement, a distance to one of the spiral nebulae, a number that placed it definitively inside the Milky Way, or definitively beyond it. Hubble got that number. He had turned his attention to the Andromeda Nebula, that faint, soft ellipse of light in the constellation Andromeda, visible to the naked eye on a clear moonless night as a small blurred glow, an object astronomers had been cataloguing and arguing about for years without being able to say what it fundamentally was. With careful photographic work on a large telescope, he found variable stars in its outer reaches. Stars whose brightness rose and fell over days in a recognizable periodic pattern. Cepheids, he measured their periods. He applied Leavitt's law. In 1923, the measurement came back at roughly 900,000 light-years. He found more Cepheids in Andromeda over the following years and confirmed the result. He published in 1925. 900,000 light-years. The Andromeda Nebula was not a cloud of gas drifting near the edge of the Milky Way. It was an entirely separate galaxy of stars, on the other side of a gulf 900,000 light-years wide. The island universes were real. Curtis had been right. The great debate was over, and the universe changed. Not physically, the universe had always been exactly the size it was, but in the minds of everyone who studied it, in the maps and the models and the professional understanding of where everything was and what everything was, the scale shifted in the span of an announcement. The Milky Way shrank from the whole of existence to one galaxy among many, and the many stretched away in all directions as far as telescopes could see. Each one an island of hundreds of billions of stars, each separated from the next by distances that made even interstellar space feel cozy by comparison. It was one of the most consequential expansions of human perspective in the history of science. One woman's law, applied to one pulsing star, had settled the question of whether there was one galaxy or countless galaxies. The answer was countless. And the number Hubble announced, 900,000 light-years, was celebrated, as it deserved to be, as the most important extragalactic distance measurement ever made. It was also wrong. The true distance to Andromeda is about 2.5 million light-years, nearly 3 times what Hubble found. Nobody knew this in 1925. The Cepheid method seemed solid. Leavitt's law was verified and real. The result was the best distance anyone had ever derived to another galaxy, and it settled a genuine scientific question that had resisted resolution for years. And yet, hidden inside the calibration, invisible, unquestioned, carrying forward through every step of the reasoning, was an error that would eventually require the entire known scale of the universe to be corrected. Before we get to what that error was and who found it, just a moment here. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. So, the crack. The year was 1952. The astronomer was Walter Baade. Baade had been doing careful, methodical observational work on stars in nearby galaxies, the kind of slow, patient work that involves looking at the same objects many times, from different angles, with different instruments, building up a picture piece by piece, without rushing toward a conclusion before the evidence is really ready. And he had been noticing, with increasing unease, that something in the distance measurements wasn't quite adding up. The specific problem was this. The distances implied by the Cepheid measurements gave a value for the Hubble constant, the number that describes the rate at which the universe is expanding. And that rate, in turn, implied an age for the universe, roughly how long it had been expanding since the beginning. But the ages of the oldest stars in nearby galaxies, stars whose ages could be estimated from their physical properties, were older than the universe the Hubble constant implied. A universe younger than the things inside it is a logical impossibility. The ladder was producing a result that couldn't be true. Something in the Cepheid calibration was off. Bade's hypothesis was about populations, about the fact that stars come in different generations, with different histories and different compositions. Younger stars, what astronomers call population 1 stars, formed from gas already enriched with heavy elements produced by earlier generations of stars, elements forged in stellar cores and scattered by explosions. Population 1 stars are the inhabitants of the spiral arms of galaxies, the regions where star formation is ongoing and the gas is chemically rich. Older stars, population 2 stars, belong to the ancient generation. They formed early in the history of the universe, from gas that was mostly hydrogen and helium, before the heavier elements had been built up in any significant quantity. Population 2 stars are found in globular clusters in the halos of galaxies, in the oldest and gravitationally settled structures. Cepheid-like pulsating variable stars exist in both populations, and this, Baade suspected, was the problem. Astronomers had been treating them as though they were the same, applying the same calibration to both, and they were not the same at all. Classical Cepheids, the ones Leavitt studied in the Small Magellanic Cloud, the ones whose period-luminosity relation she derived, are population 1 first stars. They follow her law. But there is a second class of pulsating variable stars found in the older population 2 regions. They vary in brightness, they have a period, they run on the Kappa mechanism. From a distance, on a photographic plate, they look remarkably similar to classical Cepheids. For decades, they had been measured alongside classical Cepheids in surveys of nearby galaxies without anyone clearly flagging the distinction. They're called Type II Cepheids. Their prototype is a star called W Virginis, and the class is sometimes known as W Virginis stars. And the critical difference, the difference that broke the calibration, is that at a given period, a Type II Cepheid is considerably fainter than a classical Cepheid, significantly less luminous for the same pulsation rate. Think about what that means for every distance derived from a mistaken identification. You see a pulsating variable star in a distant galaxy. You measure its period. You consult the period-luminosity relation built from classical Cepheids, and it tells you the star's luminosity. You compare that luminosity to how bright the star appears. You get a distance. But if you've actually found a Type II Cepheid and read its luminosity from the classical calibration, you've told yourself the star is considerably brighter than it really is. A star you believe to be more luminous than it actually is would, at its observed apparent brightness, appear to be closer than it actually is. The derived distance comes out too small. And because the inverse square law works on the square of the distance, double the distance, 1/4 the brightness, a significant overestimate of luminosity produces a significant underestimate of distance. Work through the math, and the result is distances that come out roughly half of what they should be. Every such measurement carried that error. Every time an astronomer looked at a nearby galaxy, identified what they thought was a Cepheid, and derived a distance from it, every time the ladder was used to climb from the Cepheid rung to the rungs above, the error came along. Baade announced the correction. The two populations had been conflated. The calibration needed to be separated and revised. And the consequence of that revision rippled outward through every rung above the Cepheids. The distance to Andromeda roughly doubled, from 900,000 light-years to about 2.5 million. The distances to all the other nearby galaxies roughly doubled. The Hubble constant, which depends on knowing both how fast galaxies recede and how far away they are, substantially revised downward. The implied age of the universe stretched outward, no longer in impossible conflict with the ages of its oldest stars. Doubled. In an afternoon. At an astronomical meeting in 1952. Not a small adjustment. Not a rounding correction. A factor of 2 applied to the entire extragalactic distance scale because a crack in the second rung had gone undetected for nearly 3 decades. This is the historical proof of what the title promised. Not a hypothetical warning about what could go wrong in theory. An actual event in the history of science, the universe doubled in size because one level of the calibration had harbored an undetected assumption that turned out to be false. Leavitt's law was correct. The pulsation periods were measured accurately. The observations were real. The method worked exactly as designed. What failed was the assumption. Perfectly reasonable, seemingly verified. Unchallenged for years, that all Cepheid-like pulsators followed the same period-luminosity relation. They don't. And the universe paid the price in the form of a scale that was half what it should have been. One crack, low on the ladder. Every measurement above it, off by a factor of 2. Baade's correction didn't destroy the method. It made it better. Astronomers now distinguish carefully between population 1 and population 2 Cepheids and apply the correct calibration to each. The Cepheid rung is more reliable after 1952 than it was before. But the history carries the warning indelibly now, and the warning is this: Even the most trusted rungs can harbour errors that are invisible from where you're standing. Errors that don't stay contained in the rung that holds them, but propagate upward into every distance above. Now, running quietly alongside the Cepheid story, providing a cross-check that became especially valuable during the years when the calibration was being questioned, there is another class of variable star worth knowing. RR Lyrae stars, named for their prototype in the constellation Lyra. RR Lyrae stars pulse faster than Cepheids, most of them completing a full cycle somewhere between 7 hours and about a day, rather than the days to weeks periods of the Cepheids. And they're considerably fainter, too faint to detect in galaxies far beyond the local group, but bright enough to be found in globular clusters and in the older stellar halos of nearby galaxies. What makes them useful as standard candles is slightly different from Cepheids. Within the RR Lyrae class, the luminosity doesn't vary dramatically with period the way it does for classical Cepheids. They pulsate at roughly similar true brightnesses across the whole class, which means the distance measurement doesn't require reading a period off a light curve and converting it to a luminosity. It simply requires recognizing the type of star. An RR Lyrae is an RR Lyrae, and that identification alone tells you approximately how bright it really is. They live in globular clusters and the old stellar halo, the same population 2 regions where type 2 Cepheids are found, distinct from the spiral arms where classical Cepheids live. Their distances don't inherit the classical Cepheid calibration. They reach the same answer through a different door. During the years when Baade was working through the 2 population problem, RR Lyrae stars were quietly consistent with the corrected, larger picture he was developing. Not the decisive evidence on their own, but a second voice reading the same answer through a different method. A cross-check that was genuinely independent. They still serve that function. When modern astronomers want a distance to a globular cluster or to a nearby old stellar system by a method that doesn't depend on the classical Cepheid calibration, RR Lyrae stars are a natural choice. Not necessarily more precise than modern Cepheid distances for the objects both methods can reach, but independent, a different stellar population, a different mechanism, a different path through the measurement problem. And independence matters enormously in a chain where each rung rests on the one below it. A hidden error in the classical Cepheid calibration, one that affects those measurements but not the RR Lyrae calibration, would show up as a disagreement between the two. It would be a signal. Baade's crack, before it was understood, was invisible in the Cepheid measurements alone. A clean, systematic comparison against an independent method might have raised questions sooner. 2 clocks pointing to the same answer is worth considerably more than 1 clock measured twice. This principle becomes more urgent with every rung you add above the Cepheids. More rungs mean more inherited uncertainty, more opportunity for a small calibration error to compound into a significant one by the time it propagates to the top of the ladder. And the top of the ladder, right now, today, in the 2020s, is where a disagreement is actively unfolding. A number that 2 of the most respected measurement programs in modern astronomy are computing through independent methods and arriving at answers that don't match. The Hubble constant, the capstone of everything the ladder is built to reach. The number that describes how fast the universe is expanding, and from which you can work backward to ask how long it has been expanding, and what kind of universe we're living in. 2 roads to that number, 2 answers, and the gap between them is large enough and persistent enough across years of new data that it has been given its own name, the Hubble tension. Is there a crack in the ladder somewhere? A subtle miscalibration in the Cepheid rung or in the rungs above it that has gone undetected the way Baade's crack went undetected? Or is the disagreement real, a genuine inconsistency between our measurements and our model of the universe, a sign that the physics we've been assuming is missing something? Nobody knows yet. Gaia is remeasuring Cepheid distances with new precision. The James Webb Space Telescope is checking Cepheid distances against independent methods, looking for any drift in the calibration that might explain the discrepancy. New supernova samples are being analyzed with increasing care. The audit is happening right now in real time by the same logic that found Baade's crack: careful comparison, independent cross-checks, following the disagreement wherever it leads. It's the most interesting unresolved question in observational cosmology, and it leads, naturally and inevitably, to the next rung on the ladder, the one above the Cepheids, the one that reaches to distances where no Cepheid can be seen, where the universe has been expanding for billions of years between the source and us, where the signal arrives as the faint light of something that no longer exists. That rung doesn't use a pulsing star, it uses a dying one. An explosion so complete, so catastrophic, that nothing of the star survives it, and so luminous at its peak that it can be seen from billions of light-years away. Bright as 5 billion suns pouring out of a single point in space in the span of a few weeks. And there's a reason, a clever, not at all obvious reason, why explosions like this can be trusted as measuring tools across the entire observable universe. That's the next part of the climb. And it comes with its own revelation. Something the astronomers who used these explosions as rulers found when they looked at the deep universe in 1998. Something that nobody had predicted. Something that changed the picture of the cosmos in a way that Hubble's discovery in 1925 had changed it, or the way Baade's correction in 1952 had changed it, fundamentally, irreversibly, and with a kind of bewildered awe that is still with us today. But we'll get there. The night is long enough. And if the pillow has been patient with you this far, if you've travelled with us from the radar echo off Venus to Leavitt's plates to Hubble's var and Baade's afternoon of double distances, then you've already climbed most of this ladder. The last rungs are just ahead, in the quiet dark, just around the next corner, exactly where they've always been, waiting without any particular hurry, the way stars wait. So, a dying star. Let's settle into that for a moment, because it's worth understanding what we actually mean when we say a star dies. Not dims, not fades quietly. Dies, in the most complete, most catastrophic sense of the word, a detonation so thorough that nothing of the original object is left behind. No remnant, no husk. Just light, spreading outward into the dark at the speed of light, carrying with it, if you know how to read the numbers, the exact distance to where that star used to be. The stars that pull off this trick belong to a particular category. They're called Type 1 supernovae. And the reason astronomers trusted them as measuring tools across billions of light-years is one of the genuinely clever ideas in all of science, not obvious, not simple, but once you see it, quietly beautiful. It starts with a white dwarf. A white dwarf is what's left of a star like our Sun after it has burned through its fuel and shed its outer layers. It's small, roughly the size of Earth, and extraordinarily dense. The kind of dense where a teaspoon of its material would weigh about 5 tons on your kitchen scale. It no longer burns, it just glows with leftover heat, cooling over billions of years the way an ember cools in a fireplace long after the last log has gone dark. By itself, a white dwarf is no danger to anyone. It sits there, it cools, and eventually, after a span of time longer than the current age of the universe, it stops glowing entirely. A black dwarf, cold and dark and invisible. But some white dwarfs are not alone. They orbit a companion star, or in some cases, two white dwarfs orbit each other in a binary pair. And over time, sometimes over many millions of years, one of them pulls material away from the other. Gas drifts across. The white dwarf gains mass. Very slowly, very steadily, it gets heavier. And there is a limit. The Indian physicist Subrahmanyan Chandrasekhar worked it out in the 1930s. A white dwarf cannot hold itself together above a certain mass, approximately 1.4 times the mass of the Sun. Below that limit, the pressure of the electrons packed inside the dwarf can push back against gravity and keep the whole thing stable. Above it, that pressure fails. The electrons can no longer hold the line. And what follows is not a slow collapse. It is a runaway thermonuclear explosion that tears through the entire star in a matter of seconds. That limit, approximately 1.4 solar masses, is called the Chandrasekhar limit. And here is the thing that makes astronomers want to use these explosions as rulers. Because the trigger is always approximately the same mass, the explosion is always approximately the same brightness. Think of it like a light bulb. If every light bulb in the world is manufactured to exactly the same specification, the same filament, the same wattage, then if you hold one up and it looks dim to you, you know it isn't a dim bulb. You know it's a far one. The dimming tells you the distance. A Type 1a supernova, at its peak, shines at roughly 5 billion times the brightness of the Sun, an absolute magnitude of around -19.3. That is a number so enormous it barely seems real. But what matters is not the number itself. What matters is that it's nearly the same almost every time, regardless of which galaxy the explosion happens in, regardless of how far away the galaxy is, regardless of how old the universe was when the star finally crossed that limit. Same trigger mass, same explosion, same peak brightness. A light bulb of known wattage, as reliable as the inverse square law allows. Almost, they're not perfectly identical. There are small variations in how bright individual supernovae get, and astronomers knew this, and it worried them, because a ruler that varies is still not a precise ruler. It's a better ruler than nothing. But it's not the kind of thing you'd want to hang the whole architecture of cosmology on. The fix came in 1993 from an astronomer named Mark Phillips. What Phillips noticed was a pattern in the light curves, the graphs of how a supernova's brightness changes over time as it rises to its peak and then fades. Some Type 1a supernovae rise and fall quickly, others stretch out their light over a longer period, fading more slowly. And Phillips found that the ones that fade more slowly are intrinsically brighter. The ones that fade faster are intrinsically dimmer. This is called the Phillips relation. And it means that if you simply watch the supernova carefully, if you track how fast its light drops off after peak, you can correct for those small variations. You can standardize the candle, measure the shape of the fade, apply the correction, and suddenly what looked like a rough measuring stick becomes a precision instrument. A slower fade means a brighter explosion. A faster fade means a dimmer one. And once you know the true brightness, you compare it to how bright it actually looks from Earth, which gives you the distance. But there is still the question of calibration, because knowing that a slower fading supernova is brighter than a faster fading one is not enough on its own. You still need to know, in actual units of luminosity, in actual watts, or solar luminosities, or absolute magnitudes, how bright a typical Type 1 supernova really is. That calibration has to come from somewhere. And the place it comes from is the rung below. The process is exactly what it was for the Cepheids before it. You find galaxies close enough for the Hubble Space Telescope to pick out individual Cepheid variable stars within them that have also, at some point in the past, hosted a Type 1 supernova. Those galaxies serve as the calibration bridge. The Cepheids, which are already anchored through parallax back to Earth's orbit and the astronomical unit, give you the true distance to the galaxy. And once you know the true distance, the observed brightness of the supernova that once exploded there tells you its true luminosity. You pin down the light bulb's wattage. And then you carry that calibration outward, to galaxies so far away that no Cepheid can be picked out, no individual pulsing star visible, no matter how long you point the telescope. You just look for the signature of a Type 1 supernova, measure its light curve, apply the Phillips relation, and read off the distance. This is calibration as inheritance. Every rung is alone taken out against the one below. If the Cepheids are off, every supernova distance is off. If the parallax that anchored the Cepheids was off, every Cepheid distance is off. And if the astronomical unit that grounded the parallax was off, if that very first radar echo off Venus in 1961 had given the wrong number, everything else in the chain, everything all the way out to the edge of the observable universe, would be wrong by the same factor. That is the ladder. And that is its fragility. Now there is a discovery that came from this rung, a discovery made in 1998 by two independent teams who had set out to measure the distance to very remote Type 1 supernovae, not because they expected to find anything shocking, but because measuring how the expansion of the universe has slowed down over time seemed like a worthwhile project. Measuring the deceleration. That was the goal. One team was called the High Z Supernova Search Team, led by Brian Schmidt and Adam Riess. The other was called the Supernova Cosmology Project, led by Saul Perlmutter. Both teams were looking at supernovae so far away that the light left them billions of years ago. And what they found when they compared the observed brightness of those distant supernovae to the brightness they should have had if the universe were decelerating or even just coasting, was that the supernovae were fainter than expected. Not because they were intrinsically dimmer, but because they were farther away, farther than they should have been, if the universe had been slowing down under gravity the way everyone assumed. The expansion of the universe is not slowing down. It is speeding up. The universe is not decelerating. It is accelerating. Something is pushing space apart faster and faster, and it has been doing so for billions of years. That something has a name, dark energy, though the name is really just an admission that we have no idea what it is. It makes up roughly 70% of the total energy content of the universe. It is the dominant ingredient in the cosmos, and we only know it's there because a ruler we built out of dead stars and a woman's discovery about pulsing supergiants told us the distances to things that had exploded billions of years ago. Adam Riess, Brian Schmidt and Saul Perlmutter shared the Nobel Prize in Physics in 2011 for this discovery. The distance ladder didn't just measure the universe, it revealed what the universe is made of. And if that were the end of the story, it would already be one of the great stories in the history of science. But it isn't quite the end. Because there are more rungs, and there is a crack that is opening right now, in the present, that none of us yet know how to resolve. But first, a few more rungs. Because the ladder has more steps than just the 4 main ones, and some of them are worth knowing about. Beyond individual Cepheid stars and individual supernovae, astronomers have developed a set of methods for measuring the distances to whole galaxies at once. One of them is called the Tully-Fisher relation. It was worked out in the 1970s, and it says this: in a spiral galaxy, a galaxy like the Milky Way, shaped like a pinwheel, the faster the galaxy rotates, the more massive it is, and therefore the more luminous it is. You measure how fast a spiral galaxy spins by watching the spread in its spectral lines, and the rotation speed tells you the true luminosity, and the true luminosity compared to the observed brightness gives the distance. For elliptical galaxies, the rounder, more amorphous kind, there is a similar relation called the Faber-Jackson relation, which links the speed at which stars move inside the galaxy to its luminosity. There is also a method called surface brightness fluctuations. The idea is beautifully subtle. When you look at a nearby galaxy, you can begin to resolve individual stars. The image looks slightly grainy, like an old photograph. When you look at a very distant galaxy of the same type, it looks smoother because the individual stellar fluctuations are blurred together by distance. By measuring how grainy a galaxy looks, you can infer how far away it is. Each of these methods is another way to extend the measurement chain outward, another handoff in the relay race. And each one is, in its own way, calibrated against the rungs below it. But there is one more independent rung worth mentioning. It goes by the name of the tip of the red giant branch, and you'll sometimes see it abbreviated as Trögerby. Red giant stars, near the end of their lives, climb in brightness until they reach a specific luminosity, determined by nuclear physics in a way that doesn't vary much from galaxy to galaxy, and then a brief flash of helium ignition kicks them off that peak and onto a different branch of stellar evolution. That peak, that bright spot at the tip of the red giant branch, serves as a standard candle. An astronomer named Wendy Friedman and her colleagues have done careful work measuring distances using the Trög method, and the distances it gives are, in many cases, slightly different from the distances that Cepheid measurements give. Not dramatically different, but measurably, persistently, stubbornly different. And that difference matters, as we'll come to in a moment. There are also measurements of a more directly geometric kind, which give astronomers a foothold on the ladder that doesn't depend on any candle at all. One of the most interesting involves a galaxy called NGC 4258, also known as M106. This galaxy contains in its center a disk of water molecules that emit microwave radiation. Water masers, they're called. By tracking the orbital motion of these masers over time, using the changing Doppler shifts in their spectra, astronomers can work out the geometry of the disk and derive the distance to the galaxy by pure geometry. The same way you'd calculate the distance across a field by measuring angles and applying trigonometry. No assumed luminosity. No candle, just angles and orbital speeds, and the distance falls out of the mathematics. That gives approximately 24 million light-years, and it serves as an independent anchor for the Cepheid rung, a way to check the Cepheid distances without relying solely on parallax. And then there is the measurement that anchored the Cepheids' very first extragalactic step. The Large Magellanic Cloud, a small companion galaxy to the Milky Way, about 160,000 light-years away, is the closest galaxy in which Cepheids can be studied in large numbers. It's the first stepping stone off our own galaxy. If that distance is wrong, everything built on top of it is wrong. In 2019, a team led by Grzegorz Pietraszewski published a measurement of the Large Magellanic Cloud's distance using a technique based on detached eclipsing binary stars. These are pairs of stars that orbit each other in a plane that happens to be edge-on to us, so that we see them passing in front of each other, eclipsing each other at regular intervals. By carefully analyzing the light curves of these eclipses, combined with the spectral shifts that tell you how fast the stars are moving toward and away from us, you can derive the size of the orbits and the sizes of the stars themselves, and from those the distance to the system, using nothing but physics and geometry. It is almost as clean a measurement as a radar echo. Pietraszewski's team measured the distance to the Large Magellanic Cloud to an accuracy of about 1%. That is the equivalent of knowing the distance from here to a city on the other side of the world to within a few kilometers. And it tightened the foundation of the Cepheid rung in a way that matters for everything above it. So, the ladder is more robust than it was a generation ago. The rungs have been checked, rechecked, cross-checked. Gaia's 2 billion parallaxes have tightened the geometric base. The Large Magellanic Cloud anchor is now known to 1%. The calibration galaxies for Type 1a supernovae have been revisited. The Phillips relation has been refined. All of this work has made the ladder sturdier. And yet, there is one more thing, the thing that should keep astronomers up at night, though the irony of that phrase is not lost on me, given where we are and what hour it is. At the very top of the ladder, astronomers can use the expansion of space itself as a ruler. If you take a spectrum of a distant galaxy and measure how much its light has been stretched, redshifted by the expansion of space during its journey to us, that redshift tells you the recession speed of the galaxy. And Hubble's law, worked out in the late 1920s, says that recession speed is proportional to distance. The farther away a galaxy is, the faster it appears to be receding. The ratio of speed to distance is a number called the Hubble constant, usually written as h0. The Hubble constant is the final rung. The calibration that turns a redshift, a mere stretching of light, into an actual distance in light years. And the Hubble constant is only as good as everything beneath it. It is the uppermost lone taken out against the chain, and so it is the quantity that is most sensitive to any error anywhere in the whole system. Here is the problem, and it is not a small one. There are two main roads to measuring the Hubble constant, and they disagree. The first road is the distance ladder itself. Adam Riess's team, working under a project called Schur's supernovae, H0 for the equation of state, has used parallax, Cepheids, and Type 1a supernovae to measure H0 at approximately 73 kilometers per second per megaparsec. What that means in plain terms is that for every megaparsec of distance, roughly 26 million light-years, a galaxy appears to be receding about 73 kilometers per second faster. That number, 73, is what you get when you climb the ladder. The second road goes in the opposite direction. Instead of building up from nearby measurements, it starts at the very beginning, the early universe, just 380,000 years after the Big Bang. and reads off the Hubble constant from the pattern of temperature variations in the cosmic microwave background, the faint afterglow of that early fireball. The Planck satellite, a European Space Agency mission that mapped the CMB with extraordinary precision, combined with the standard model of cosmology, gives a Hubble constant of approximately 67 kilometers per second per megaparsec. 67 versus 73. That might not sound like much. It is not a small gap. The two measurements are separated by a difference that is, statistically speaking, significant, several standard deviations. The kind of gap that in physics does not go away when you take more data. It gets more persistent, more stubborn, more uncomfortable. This disagreement is called the Hubble tension, and it is one of the most actively debated problems in cosmology today. There are two possibilities, and neither of them is comfortable. The first is that there is a crack in the ladder. Some systematic error somewhere in the chain, perhaps in the calibration of the Cepheids, perhaps in the way the Phillips relation is applied to distant supernovae, perhaps in some subtle way that has not yet been identified, that is making the ladder give a number slightly higher than reality. Walter Baade's discovery in 1952 looms here like a cautionary ghost. He found a crack nobody had suspected. The universe is large enough and subtle enough to hide another one. The fact that Wendy Friedman's Trög B distances, a completely independent ladder rung, not relying on Cepheids at all, give a Hubble constant of roughly 69 to 70, somewhere between the two main numbers, suggests that at least part of the tension might live in the Cepheid calibration. But the Trög B number isn't perfectly settled either, and it's been revised as more data comes in. It is not yet a clean resolution. The second possibility is that there is no crack in the ladder. The ladder is right. And the problem is with the early universe road, or more precisely, with the cosmological model that's used to translate the CMB pattern into a Hubble constant. That model assumes certain things about what the universe is made of and how it evolved. If any of those assumptions are wrong, if there is new physics, some ingredient the model doesn't account for, then the CMB road might be giving the wrong answer, and the universe might genuinely be expanding faster than the standard model predicts. New physics. Something missing from our picture of the cosmos. Right now, both the James Webb Space Telescope and the Gaia mission are being used to re-examine the rungs of the distance ladder with fresh eyes. JEST has been checking Cepheid measurements in the same galaxies that anchor the supernova rung, looking for any sign that crowding of stars, dust, or calibration errors might have biased the numbers. Gaia has been providing ever more precise parallaxes for the Cepheids in our own galaxy, tightening the foundation. New Type 1a supernova samples are being analyzed. New techniques are being applied. The ladder is being audited, carefully, in real time. And as of the mid-2020s, no one has found the crack. It hasn't gone away. The tension sits there, unresolved, at the center of cosmology, like a question someone asked at a party that nobody has been able to answer, and everyone is too polite and too interested to simply change the subject. Which is, if you think about it, exactly as it should be. A frontier isn't a frontier if everyone already knows what's on the other side. So that is the ladder. From bottom to top, a radar echo off Venus, timed with the speed of light, giving the width of Earth's orbit. A blink of that orbit against the distant stars, giving the distance to the nearest few thousand light years. A pulsing star whose heartbeat declares its true brightness, carrying us to Andromeda and beyond. A dying star that always detonates at the same mass and shines with the same ferocious light, carrying us across billions of light years. And at the very top, the expansion of space itself, stretching the light of every galaxy according to a constant we're still arguing about. Rung by rung, lone by lone. Now take a moment, if you're still with me, and no hurry if you're not, to consider the scale of what this chain of tricks has given us. The observable universe is approximately 93 billion light-years across, a radius of about 46.5 billion light-years in every direction. That number is larger than the age of the universe times the speed of light, which might seem impossible if the universe is about 13.8 billion years old. How can we see anything farther than 13.8 billion light-years? The answer is that space itself has been expanding all this time, carrying distant objects with it, so the light that left them long ago has had a much longer journey than the straight-line distance would suggest. 93 billion light-years. That is the horizon of our observable cosmos. And that number, that vast, nearly incomprehensible number, is the product of a chain that begins with Earth's orbit, a distance that light crosses in about 8 minutes. A baseline of 2 AU, about 300 million kilometers, which is itself roughly 1/500th of a light year. The smallest effective ruler in the whole ladder, from a baseline of 8 light minutes to a horizon of 93 billion light years. A chain of methods spanning a factor of roughly 10 to the power of 17, a 1 followed by 17 zeros, in distance. And it was never crossed. No one travelled it with a tape measure, no one flew to Andromeda. No one waited at the far end of a Type 1 supernova to read off the number. We did it the only way it could be done, by being clever, by being careful, by building each rung on the one below it, and by being honest enough to notice when the rungs didn't quite fit together. Eratosthenes measured the shadow of a stick in 2 cities to find the size of the Earth around 240 BC. That was the first rung of the first rung, the foundation of the foundation. And the chain that began with a shadow in Cygni runs, unbroken, through Venus transits and radar echoes and photographic plates and photomultiplier tubes and digital cameras and space telescopes, all the way to the edge of what we can see. It runs through the life's work of a woman paid 30 cents an hour who was not allowed to follow her own research, and whose law about pulsing stars is the reason we know how big the universe is. Henrietta Swan Leavitt's period-luminosity relation is in every extragalactic distance measurement ever made. It is in the number 93 billion light-years. It is as load-bearing as anything in science, and she did not live to see how far it would carry us. It runs through a night in 1923 when Edwin Hubble stood at the eyepiece of the Hooker telescope on Mount Wilson and circled a faint blinking star on a glass plate and wrote var in pencil. The moment the known universe expanded from one galaxy to countless galaxies. It runs through Walter Baades' Afternoon of Arithmetic in 1952 when everything doubled. A reminder, in case the reminder is ever needed, that the universe is under no obligation to fit our expectations. It is as large as it is, and it will tell us so in its own time when we build the right instrument and ask the right question. It runs through 1998 through 2 teams of astronomers who found their distant supernovae dimmer than expected, fainter than decelerating expansion allowed, and had the courage to say what that meant. That the universe is not slowing down, that something is pushing it outward faster and faster, something we cannot see, something that makes up the majority of the universe's energy, something we call dark energy because we have not yet found better words for it. And it runs through right now. Tonight, through the James Webb Space Telescope, floating at the second Lagrange point, looking at Cepheids in galaxies 80 million light-years away, trying to decide whether the crack is in the ladder or somewhere deeper. Through Gaia, still sending back measurements of 2 billion stars, still sharpening the base of the chain. Through the papers being written and argued over and revised and re-argued in the offices and cafeterias of every observatory on Earth and several that orbit above it. The ladder is not finished. It is still being built. That is the honest answer to the question the video title asked. How did we figure out the distance to everything in the universe? We built a chain of increasingly clever tricks, each one borrowed from the last, each one only as trustworthy as the rung it stands on. We got it wrong at least once in a spectacular way, and we found out, and we fixed it. We are probably not done finding out. And the number at the top of the chain, the Hubble constant, the expansion rate of everything, is still, as of tonight, a number we argue about. Which means we are still in the middle of figuring it out. Not at the end of a story, but somewhere in the long, ongoing middle of one. And that, I think, is one of the best things about it. Because a cosmos that still has open questions is a cosmos worth getting up in the morning to think about, or staying up, as the case may be, though I have been trying very hard not to keep you that way. Wherever you are listening from tonight, whether it's a bedroom with the curtain letting in a sliver of streetlight, or a couch with the television off and the house finally quiet, or somewhere else entirely, the universe outside your window is approximately 93 billion light-years across, and expanding. Every galaxy beyond the local group is moving away from us, its light stretched a little redder by the journey. The photons that reach your eyes when you look at a clear sky left their sources years ago, thousands of years ago, millions of years ago. The light from the Andromeda galaxy, that faint smudge you can just barely see on a very dark night, left there 2.5 million years ago, before our species existed. You are not looking at the universe as it is, you are looking at it as it was, across a span of time so large that the difference between the nearest stars and the farthest is almost unfathomable. And yet, we know how far. We worked it out. With geometry and patience and stubbornness, and, in one crucial case, with a woman cataloguing plates of glass in a room in Cambridge, Massachusetts, finding the heartbeat of the universe in the numbers she was paid 30 cents an hour not to think too hard about. We know how far. That's a good thing to carry into sleep, if you can. The universe is enormous, and we know how enormous, and we know because we figured it out one clever step at a time, building the ladder as we climbed it, never losing grip of the rung below. I hope the pillow is comfortable. I hope whatever is on your mind tonight has softened a little, the way things do after midnight, when the house is quiet and the breathing slows. You don't have to hold on to everything we talked about tonight. The ladder will still be there in the morning. The parsecs and the Cepheids and the Chandrasekhar limit, all of it will wait. That's the nice thing about the universe. It's patient. If this slow journey through the dark was any comfort to you, a like and a subscribe would mean a great deal to this little channel. Small creators like me rely on your support to keep these nights going. And if you feel moved to leave a comment, I'd love to know where in the world you're listening from tonight and what time it is in your corner of the dark. Thank you for being here. Thank you for travelling this far. Good night, kiddo. Grandpa'll leave the porch light on.